Hi everyone, and welcome to the first of two videos going through some past exam questions on the topic of the equilibrium constant, Kp. The first question we've got here is a multiple choice one. They've given us this reversible reaction. We've got the numbers of moles, and it's just asking us to work out what the mole fraction of H2 is. So to work out the mole fraction, remember it's just the number of moles of H2 in this case, divided by the total number of moles. So we just need to work out the total number of moles. So we're going to do 0.32 plus 0.96 plus 0.12. You work that out. So the total number of moles that we've got is 1.4. And then we're just going to do the number of moles of H2 divided by that. And we get 0.69. Oh, it's going to be 0.686, so it's going to be B. Okay. Right, for the second part here, ammonia can be made, so it's the same reversible reaction as we've got above. It is actually a different question, but it's actually looking at the same equation. It's giving us various bits of information here. What effect will increase in the temperature have on the composition of the equilibrium mixture and on the value of the equilibrium constant? Okay, so if we've increased the temperature, then according to Le Chatelier's principle, the equilibrium is going to shift to decrease the temperature, so it would shift in the endothermic direction. This is showing us that delta H is negative, so the forwards reaction is exothermic. So therefore, the backwards reaction is endothermic. So increasing the temperature is going to shift the equilibrium to the left. So if we say the forward reaction is exothermic, so increasing the temperature will shift the equilibrium to the left. And what effect is that going to have on the composition of the equilibrium mixture? So the equilibrium mixture, if it's shifted to the left, then it's going to have more N2 and H2. And less NH3. And so if we were going to write the equilibrium constant, remember the equilibrium constant is always products over reactants. So if I've got more reactants, less products, then the value of the equilibrium constant is going to decrease. Okay, because I'm dividing, I've got a small number on the top and big numbers on the bottom. So the equilibrium mixture will contain more N2 and H2 and less NH3. So the value of the equilibrium constant will decrease. Okay, and then we've talked about what's in the equilibrium mixture and we've talked about the value of the equilibrium constant. So we've ticked off the two things that it wants us to do. So we're going to get 2 marks. Okay, if we then have a look, this question moves on to do a calculation. So it then says, chemist is mixing together a certain amount of N2 and a certain amount of H2. So we're still looking at the same equation here. Mixture is heated, it's allowed to reach equilibrium, and they're giving us some information there, and it just wants us to calculate Kp. Okay, so we're going to start by writing the equation out. That's the equation that they had before, if I just put that here. All right, and then the way that we're going to do this is we're going to set this up in a table. Okay, remember the standard method of doing these kinds of questions is in the ICE table, as they call it. So initially, what do we have? How does it change? And then what do we have at equilibrium? Okay, so initially it's telling us 0.45 moles of N2 and 0.45 moles of H2. And it doesn't tell us about the NH3, so we're going to assume that that's 0 to start with. At equilibrium, it contains 0.4 moles of N2. Put that in the right place, yeah. So that's here. So therefore, the change is minus 0.05. Therefore, the change in the H2 well, it's a 1 to 3 ratio, so that's going to be minus 0.15. Okay, it's going to change by 3 times as much. So this is going to go down to 0.3. And in NH3, it's a 1 to 2 ratio here. So this is going to be 0.1, and it's the product, isn't it? It's been produced, so it's going to be plus. So we're now going to have 0.1 moles at equilibrium. Okay, then we actually want to calculate Kp. So let's write the expression for Kp. It hasn't actually asked us to do that, but it would be useful. So it's going to be the partial pressure of the NH3 squared over the partial pressure of the N2 and the partial pressure of the H2 cubed. So we need to work out the partial pressures then. So therefore we need to know the mole fraction is the next thing that we want to do. And then we're going to work out the partial pressure of each of these. So let's add up the total. So the total number of moles, 0.4, 0.3, it's 0.7, 0.8. So we have a total of 0.8 moles. So the mole fraction, remember, is just the number of moles divided by the total. So 0.4 over 0.8 is going to be 0.5. That's 3/8. 0.3 divided by 0.8 is 0.375. And 0.1 divided by 0.8 is 0.125. Right, and then to work out the partial pressures, remember you just do the mole fraction times by the total pressure. Okay, so we're just going to multiply each of these by 500 kilopascals. So 0.5, that's going to be 250. 0.375 times 500 is 187.5. 0.125 times 500, 62.5. So these then are the partial pressures. We're now going to substitute them into our expression. We need to make sure we get them in the right places. So we want NH3 on the top, and that needs to be squared. So Kp is going to be 62.5 squared over N2, which is 250, times 187.5 cubed. So let's work that out. So we've got a horrible looking number here, 0. Blah, blah, blah. We need to put that needs to be in standard form, that's awful. So we're going to call it 2.37 times 10 to the, 1, 2, 3, 4, 5, 6, minus 6. Okay, and then the units, we're going to substitute units into this expression. So we're going to say we've got kilopascals. Those are the units they've given us, so we'll just carry on using those units. Okay, we don't need to convert it into pascals or convert it to atmospheres or whatever, just leave it in whatever units they've given you. So it's going to be kilopascals squared over kilopascals times kilopascals to the power of 3. So it's squared over to the power of 4. So we're going to end up with kilopascals to the power of minus 2. Finally, just to finish this off, we've got another multiple choice question here at the end. A mixture of N2 and O2 has a total pressure of this many atmospheres. The mole fraction is 0.7. What's the partial pressure of oxygen? Okay. So the first thing we can say is, look, if the mole fraction of N2 is 0.7, so therefore the mole fraction of O2 is 0.3. Because the mole fractions have to add up to 1. So then the partial pressure, we just need to do 0.3 times by the total pressure. Okay. and we get 0.426 atmospheres. So therefore, it's B.